Right, so in this video, we're going to be looking at discrete dynamical systems. These are systems of equations that are changing over time, measured in discrete units, so per day, per month, per year, that sort of thing, rather than evolving continuously. The continuous case is handled in differential equations, but when they're discrete, then we can handle them in linear algebra. In addition, we're going to be looking at examples that are linear so that they can be modeled with a matrix. One common example is a predator-prey model, where one species, the predator, survives by consuming the second species, the prey, and the prey reproduces to replenish the species. The rate at which the prey is consumed by the predators can change the stability of the system. If the predators eat the prey faster than the prey can reproduce, then the population will collapse. If they maintain more of a balance, then it's possible that both can grow at the same time. There are many examples of such system that have only a few number of variables, but we're going to be considering examples such as the chemical reaction models, where we need two or more variables to describe the system. Now, Markov chains are a kind of discrete dynamical system with extra properties where the matrix entries are representing probabilities. That is going to be considered in another video, another discussion, but everything that we're going to talk about in this video applies to all discrete dynamical systems, not just Markov chains. All right, so we're going to consider the problem geometrically, and then we'll discuss some specific applications. So first, we want to consider a system of at least two, but potentially more variables that change over time according to a linear function. And the relationship is that we have some change of state matrix A multiplied by our initial state vector, x sub k, and then that gets modified when you multiply them together into being the new state matrix, x sub k plus 1. Now, a sequence of such steps, x sub 0, x sub 1, x sub 2, etc., is called a trajectory. So we're going to consider the system of differential equations below. It relates an A variable and a B variable. So, species A, species B, perhaps, and we're going to plot 10 trajectories, 10 points of the trajectory given the initial state vector 520. So this is our system of equations. We can write this as a matrix by pulling out our coefficients and putting them into matrix form. And then we will simply, in order to get the next step and the next step in the trajectory, we will multiply our current state vector by the change of state matrix. So here, if we take our A matrix and we multiply it by our initial state vector 520, then we can do a little bit of matrix multiplication, and we find that our new state vector at stage 1 is now 11 and 23.5. And then if we want to find the next stage in our trajectory, we'll then multiply that vector, the one that we just got, by the change of state matrix. And when we do that, we end up with the second state being 13.95 and 25.05. And as we continue along, continuing these calculations, we get the sequence of vectors shown here on the screen. So we can see that our predator population, if we can think of that as usually the first population in the model, with a lower replenishment rate, let's say, they typically, in this example, they are increasing for a time, but then they reach a maximum just below 16, and then you can see they start to decline. Likewise, you can see that the second population also starts increasing up to a point right here, and then it also begins to decline. And so if we plot these points in sequence, then we get this graph shown here, where we're jumping from point to point, x1, x0, x1, x2, x3, etc., following the dots. Now, to obtain the trajectory with the fewest number of keystrokes here on your calculator, you want to enter the matrix into your matrix A and the state vector into matrix B. Then multiply A times B on the calculator screen as shown. That produces your second state vector. And then multiply matrix A by the answer, like so. And then that will produce the next state vector. And then from that point, you can just keep hitting enter, 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 and it will produce the states, the vectors that we listed above. Now, the answer key is the second, and then the minus C, not the subtraction key, but the negative key. And then again, just keep hitting enter until you obtain the sequence. Now, we can plot the points by going to the stat menu and then going to edit and entering the first components in list 1 and the second components in list 2. And then when we want to see the graph, we can go to second y equals. From here, we're going to turn the stat plot on. And then within plot 1, we're going to select the line graph option, which is the second one. And then you can choose the mark at the bottom. List 1 and list 2 are there by default. So if you're using list 1 and list 2 for your x and y coordinates, or in this case, our A and B coordinates, you don't need to change these defaults. You can choose the mark. I use the squares in my particular graph, but those are fine. You can use any of these. And then finally, when you've entered all of this information, select Zoom 9 for Zoom Stat, and it will adjust your windows so that you can see all of the points on the screen. Of course, you can also plot them by hand if you prefer. Now, in this case, the model is interesting because it appears that both variables increase at first, but then after some time, they both begin to decline. And we're interested in the long run behavior of these systems. And we don't necessarily want to do it by plotting 100 points of the trajectory. So in order to understand how this system is going to behave in the long run, we're going to need to find the eigenvalues and eigenvectors of the matrix A. So to do that, here is our matrix A again. And so to find the eigenvalues and eigenvectors, we're going to subtract lambda off the diagonal. And then we're going to find the determinant. And we end up with this equation right here. Do not be terribly surprised if you have to use the quadratic formula to factor these, because we're dealing with decimals after all. And when you apply the quadratic formula to solve for lambda, we end up with two eigenvalues. One is 0.979 and the other is 0.52087 approximately. Both of them are less than 1, and that's important for understanding the long-term behavior. Now, we do have to be somewhat careful finding the eigenvectors of the matrix, since we're going to end up with a square root, and rounding errors will make it impossible to solve and reduce this matrix in our calculator. So fortunately, there are only 2 variables, and so we can do this without like row reducing in our calculator. But if you have multiples of 3 or more variables, you will have to do the arithmetic by hand. It is terrible and irritating and inconvenient, but if you try to put these in the calculator as decimals, square roots of decimals, the rounding errors in the calculator will almost certainly treat your matrix as an independent matrix and not as a dependent matrix. And so it won't help you at all. So we're going to start with the larger lambda value, and we're going to use the value we obtained, not in decimal form, but here in the 1.5 plus or minus the square root of 0.21 all over 2. We're going to use the positive version to start with. Again, you may recall from dealing with square roots and complex eigenvalues that once we find one eigenvector, we can find the other one by just applying the conjugate. So that also works for square roots. So we'll use the positive one, and I'll substitute that into my equation. Now, and then if we do a little bit of arithmetic to simplify, we end up with this. Now, as noted, what often happens with these, you'll see this in complex examples as well. These two entries here look almost the same, except the real part sign is flipped. This is an indication that this is in fact dependent. We could do some arithmetic to verify it, but it is in fact the case. And so we can just choose one of our equations to solve, and I will choose the second one typically so that I don't have to divide by square roots. So if I take that out of my matrix, I get negative 0.5 x1 plus this crazy number times x2 is equal to 0. I'm going to move everything over to the other side, and I'm going to end up with this number divided by this number, and that is my coefficient of x2. If I put this now in my calculator, I can estimate the eigenvector as 0.642 x2. And so if I let x2 be 1, then x1 is this number right here. Now I can solve for the second eigenvalue because it's just the conjugate of the first one. And when I simplify this expression, I'm going to get 2.496 x2 approximately. And at this point, it's safe to go back to decimals. It'll make the most sense when we try to plot things rather than use the exact values. But our eigenvector now, if x2 is 1, then x1 is 2.496, again, approximately. Now we can plot these on our graph. Essentially, remember that the slope is the change in x over the change in y over the change in x. The change in y here is 1. The change in x here is 2.496. And so we can plot, or we can plot this as a parametric equation. That's also possible to plot them like that. But what we know from our relationship with the eigenvectors is that the relationship between xk at any point in time is actually related to the eigenvectors and a coefficient. We can, because we have two eigenvectors for our matrix, that can form a basis for our space, and therefore we can represent any vector in the plane as just a linear combination of our eigenvectors. And then if we start out, let's say, representing x sub 0 in this form, then when we apply the matrix A, then the next step along the way is simply going to be multiplying the first eigenvector by lambda 1 and the second eigenvector by lambda 2. That's how it's adjusting that linear combination. And so if you proceed n steps along the way, then you have lambda to the n times your eigenvector and lambda 2 to the n times your second eigenvector. Now, this is the relationship that we need in order to understand how the behavior of the system is going to be changing. So if our lambdas are 1 or larger, then this component will persist in our final solution. Whereas if we're taking a number less than 1 and raising it to a large power, then that's going to eventually disappear because fractions multiplied by fractions get smaller over time. We saw with our particular example that one of them was close to 1, And so but still less than 1. And that is going to decay very, very slowly over time, but still, nonetheless, eventually shrink. Whereas in the lambda 2 case, that was closer to a half, and that's going to decay much more rapidly. And so we actually see that behavior consistent with our trajectory. Here I've plotted my 2 eigenvectors on my graph and my trajectory of values. And you can see that given this trajectory right here, this is the one that corresponds to the larger eigenvalue. Over time, you can see that any component that is not related to my larger eigenvalue disappears, and the trajectory begins to merge with just following this trajectory, this path along the way to the origin. If we were to continue plotting additional points, they would all fall closer and closer and closer to this line until they disappeared entirely. Now, if lambda is greater than 1, then what this will do is it will grow without bound. If it's equal to 1, then as what happens in the Markov chain examples, again in another video, they will have an equilibrium vector and will remain stable over time. So the trajectory will actually approach a point and then it will stop there. Now, if it's equal to -1, it will oscillate between 2 values, but it will still remain otherwise stable in this orbit of 2 values. But again, if it's less than 1, this will decrease over time and it will drive the system to 0. Now, each of these examples has a special name. In the example that we were doing, this is called an attractor or a sink. Since both of the lambdas are less than 1, the trajectory will drive the population in both cases to 0. If we have a situation where one lambda is less than 1 in absolute value and the other is greater than 1, then the origin is called a saddle point, because there will be some trajectories that attract it to the origin, and then there will be at least one trajectory that repels it from the origin, or vice versa. And the behavior of the system will then be dependent upon the eigenvalue that is the largest. If they're both larger than 1, then the origin acts like a repeller or a source, and both of the populations will increase without bound. Now, if you have a saddle point, then trajectories will tend to behave something like this, where they will appear to approach the origin, but if they're not exactly along the trajectory that leads directly to the origin, then the larger eigenvalue component will take over as the smaller one shrinks, and then you will eventually be dragged toward going away from the origin along the trajectory or near the trajectory of the larger eigenvalue. Now, in the special case of a Markov chain, one eigenvalue is equal to 1, and so that is what produces an equilibrium or steady state solution. But that is not the case in most of the discrete dynamical systems we will be looking at. We also briefly mentioned that if one of the eigenvalues is -1, then you will get an oscillation. It will be a stable oscillation, but it will be an oscillation between 2 values. This is very uncommon in a predator-prey relationship, but at least mathematically it is possible. Now, plots like this one that we see right here, these are sometimes referred to as phase portraits. The trajectories here are plotted according to the eigenvectors, and then whether the arrows point toward the origin or away from it is going to depend on the sign of the eigenvalue. So if the eigenvalue is less than 1, then this is dragging it toward the origin, because less than 1 raised to a power gets smaller, whereas if the eigenvalue is greater than 1, greater than 1 raised to a power gets bigger, so then the trajectory arrows along the eigenvector here will point away from the origin. So in the case of a repeller, we would have, say, two arbitrary eigenvectors here, and we would have arrows pointing away from the origin in both directions. If you have an attractor, then you will again have two, these are arbitrary eigenvectors, and they are pointing all the arrows toward the origin. If you have one equilibrium, then you will have, for instance, one lambda in this case is less than one. It will drive toward the origin, but as this component decreases, you will essentially go towards some point on the stable equilibrium vector, which you'll notice has no arrows here. If the lambda is equal to -1 instead, again, you'll have this trajectory that does not have any arrows on it because it's stable. The one that's less than 1 points toward the origin, but what you'll have is that even steps will appear on one side and odd steps will appear on the other side. You'll still get this behavior where the trajectory will approach a point on this eigenvector, but nonetheless, it will flip back and forth. Now, one other kind of situation we can encounter is the situation where one of the eigenvalues of the matrix are at least one. I mean, they have to come in conjugate pairs. So, but in the 2x2 case, where all of the eigenvalues of the matrix are complex. So let's walk through an example where the discrete dynamical system has complex eigenvectors. In this case, we changed one of these components here from, it was -0.5, I believe, to now it's -0.7. Let me just double check. Yes, it was originally -0.5. And so we've just made that -0.7 instead. Now we're going to initially proceed the same way that we did before, of course. We're going to subtract our lambdas along the diagonal, come up with our characteristic equation, and we get this. Again, not obviously factorable, so we throw it into our quadratic formula, and we end up here with the square root of -0.19. And if we simplify this expression a little bit, so that we can look at it in decimal form, we get 0.75 plus and minus 0.2179i. Now, this is obviously no longer real, so we can't plot these graphs. We don't, when we try to find our eigenvectors, the eigenvectors aren't going to be real either. And so we can't graph them on a real graph. They're not straight line trajectories anymore. But we can still see what happens to the equation over time. And if we start with that same initial starting point that we had in our previous example, 520, and then we multiply by the matrix, we get 11 and 22.5, and then we multiply by the matrix again and again and again. If we continue plotting this, what we end up with is this trajectory. But if you zoom in, it doesn't actually go to the origin exactly. It's going to go past the origin and actually spiral around the origin. Now, because our real component of our eigenvector, if we go back up here, 0.75, actually, it's the magnitude, sorry. The magnitude, if you calculate the magnitude of this vector, it is still less than 1. And so the trajectory is still collapsing. It is still, the population is going to 0. But it is actually spiraling around the origin. You can see here, eventually we're actually getting negative values because we're going right past the origin. When you get complex eigenvalues, you do get this essentially spiraling behavior. The magnitude of the eigenvalues is going to tell you whether it's going to go to the origin, or whether it's going to be a stable orbit, or whether it's going to go off to infinity. So we can still characterize the origin as being on a tractor or a repeller, but it will never be a saddle point. So here, if we find the magnitude, we can actually calculate it. We end up with 0.78 approximately. So less than 1. So again, this is spiraling in toward the origin. If this was greater than 1, that would be spiraling away from the origin. And again, if it was exactly equal to 1, then that's when we would get a stable orbit. We would just go around in a circle. Now, if we want to, we can analyze this a little bit further and we can figure out the rate of rotation. So there is a similarity transformation for complex eigenvalues where we put our components into our matrix like so. And by scaling this, we can actually find out the angle of rotation. And in this particular case, we end up with something about 16.2 degrees of rotation each time you multiply by the matrix. So that's tells us how quickly we're spinning around, again, about 0.28 radians. Now, in this example, I calculated both the sine and the cosine separately, and both gave me positive values, so I know that it is a first quadrant acute angle. Now, as I said, if lambda is greater than 1, then the graph is going to spiral outward like this. We would indicate the path of the trajectory again with arrows indicating we're going away from the origin. And where lambda is equal to exactly 1, we get a periodic orbit. Even if it doesn't replace actual, like doesn't fall on exact values each time it goes around, the distance from the origin will remain constant.